We're now going to move away from looking at geometric entities as abstract types and talk about representations of those entities. We were able, at least with our what are called the coordinate-free method, to look really at a number of geometric principles which hold regardless of the representation. But at some point, what you have to do is say, well, where is this? And I can't say it's next to something or it's above something. Concepts that I get from just the basic geometry. I need to say where its location is, what its address is, what its x, y, and z values are. And so that's where representation comes in. And we're going to start with representation today, and then we're going to move into talking about transformations, both as a way of changing representations, but also doing things to our objects. We'll see that that's equivalent. That if you do an operation like a rotation on something you're working with, that's equivalent to doing a change of coordinate systems, or what's called a change of frames. So we're going to introduce first in this lecture the concepts such as dimension of a space and getting basis vectors and for that space. And then we'll also look at the difference between vector spaces and their representations and frames and their representations. We'll see that because we need more than what's in a vector space, which is just vectors and scalars. Remember we added points to get what's called an affine space. That's called a frame. So we'll need to talk about how we change frames and how do we change the basis vectors in those systems. Okay, so let's start with this notion of linear independence. And we remember with vectors we have this property of scalar vector multiplication, which always gives us another vector, and we can add two vectors. So this sum alpha 1 v1 plus alpha 2 v2 always makes sense. It's a vector plus a vector plus a vector. And we say, well, what is the meaning if that adds up to 0? And 0 here meaning the 0 vector. Well, that's where the concept of linear independence comes up. If you can find some summation of a bunch of vectors multiplied by scalars and it sums to 0, and not all of those alphas are 0, that says I can solve that equation for one vector in terms of the others. So if, say, alpha 1 was 1, just to make it easy, and v1 plus v plus the sum of some others, which not all of which are 0, is giving you 0, then I can just move the others onto the other side of the equation, where minus v2, remember every vector has an inverse vector which just points in the other direction. I've now given a representation for v1 in terms of some of the other vectors, and therefore v1 would not be independent of all the others. But if the only way I can get this sum to be 0 is if I make all the constants in front 0, then these vectors are linearly independent, which simply means there's no way to solve that equation for any of those vectors in terms of the others. So in a sense, it's the minimal number that you need to be able to represent an arbitrary vector in terms of some given set of vectors, v1, v2, v3, and so on. Now, it turns out that this number that you get is called the dimension of the space, and it's independent of which of these vectors I pick. It's a property, really, of the space. So here's formal definition of dimension, and it's the maximum number of linearly independent vectors that I can find, and that's the dimension of the space. So in n-dimensional space, you can find n linearly independent vectors, and they're called the basis for the space because with them I can form any other vector. See, if I take any other linear combination with another vector, I can always solve it for that vector. Given a particular basis, say v1, v2 through vn, then any other vector, as I just said, could be written that way for some set of alphas, and those alphas turn out unique. These are little problems they give you to solve in a class on linear algebra. So this concept of basis is really is really crucial. And if you think about it, you've done this a lot whenever you look at a coordinate system. You have something pointing in the x, the y, and the z direction in 3 dimensions. You say, oh, that's my basis. But there are many other bases, and what we want to talk about now is things that how we change these bases, and that's the direction we're going in. Now, I want to give you another concept here, because at this point, v1, v2, and v3 are still abstract vectors. We haven't said anything about what they are or what kind of space it is. They could be velocities, they could be directed line segments. We're just saying that if it's a 3-dimensional space, there are 3 basis vectors, no matter what those vectors ultimately mean. And we're going to say that the alphas then are the representation of a given vector with those 3 basis vectors. So we're introducing now the concept of representation. And why do we need it? For the reasons I said a few minutes ago. You need some way of really specifying where something is if we can agree on what that basis set of vectors is. Okay, so now we're going to really get away from this sort of more abstract space into something that's maybe closer to what you've done before, in particular when you did Cartesian geometry. Now, that's going to get us to the notion of a coordinate system, and you've already seen 2 of them, which I think have been in our problems and are important. And obviously, it's the object or world coordinate systems where we specify our objects, and then we talked about camera coordinates, which is what the WebGL wants to see everything represented in. So we have at least 2. We sort of know there's these others at the other end. We talked a little bit about clip coordinates that goes in the middle that is used after the shaders, after the vertex shader, and then eventually there's the coordinate system for what goes up on the display. So we have multiple reference systems that we use, and I think it's easy to see that we're going to have a way of going back and forth between them. And now we want to tie that to the notion of basis. Okay, so a coordinate system now is for a vector space. We're not talking about points yet. Nothing I've said yet has to do with points. But let's start with a coordinate system, and it's in some number of dimensions. If you want to just say it's 3 dimensions, that's fine, because all of this holds in any number of dimensions. So if I give you a basis, v1, v2, vn in that space, any vector can be written as some linear combination of scalars times those basis vectors. And the scalars, if we take them alone and say, well, look at this group of scalars, I can form a little n-tuple out of them, alpha 1 through alpha n. They're said to be the representation of that vector v. But the important thing is this thing at the end. It's always with respect to a particular basis. That's really what's crucial here. That v is a vector in space. It can be represented with any basis vectors that I give you, as long as we agree. If it's an n-dimensional space, I have n basis vectors, but I have an infinite ways that I can come up with basis vectors. So when we say that this group of scalars is the representation, it's always with respect to a given basis. Now I could use a little very simple algebra, matrix algebra, to do that. If I write the alphas as a column where T is the transpose operation, and I multiply it, this equal is really a multiply here, times, oh boy, this is really, okay, oh, I know what I'm doing, sorry, let me go backwards. We can write this as alpha 1 through alpha n, write it as a row or write it as a column. Usually our basic one is going to be a column, so I'll say I'll write it this way, alpha 1 over alpha 2. But if I take the transpose of that, I get alpha 1, alpha 2, alpha n, and they represent the same thing. So what I'm saying is that then I can I'll use a boldface A to say I'm using this column or row matrix representation of alpha, just a little shorthand for that. So here's a really simple example of that. And so if I have some vector in v1, v2, v3 of the basis, and I look at 2v1 plus 3v2 minus 4v3, then this this little row matrix A is 2, 3, minus 4. Now I want to say one thing about this. There's a lot about this using these words row vector and column vector, which I try to use in the book. Row matrix and column matrix instead of a column vector and a row vector. The problem is that vector is used in two different ways. If you're in the physical world, then a vector is, as we've said, something with magnitude and direction. If we're talking about linear algebra, then vectors mean usually a row vector or a column vector, which is a 1 by n or an n by 1 matrix. And this causes all kinds of confusion that we're going to see more of in this lecture and next lecture. So I try real hard to say if I'm talking about this kind of thing where there's just an n tuple or 3 tuple here, and it's written as a little row matrix. I try and say row matrix instead of row vector, but I switch a lot. Generally, you'll get it by the context, but there are some differences between the terminology in that case. Okay, so let's now talk about a little more about coordinate systems and changing it. So we're going to start with our representing vectors in object coordinates, but then we're going to need to move them on to camera coordinates and clip coordinates and eventually screen coordinates. Now, the problem with vectors is they really have no position. We talked about that in last week's lecture. So suppose I take this very simple diagram that you should all be familiar with. I mean, here's the way we usually draw our what we call our coordinate axes, and here's some vector, the little arrow up here in that space. And often what we'll say is, oh, our basis vectors are this one pointing in the x direction, this one in the y, and this one in the z. And here's how I represent, I can find out a representation of v as some linear combination of the x, y, and z vectors. Now the problem is, if these have no position. So if you look at the diagram on the right, it's exactly the same. All I've done is move them around with the idea this is still pointing in the z direction, this is still pointing in the x and the y and the z. And this vector here is exactly the same as it was here. So anything I write, which might be something like v is 1 times the unit vector in the x direction plus 2 times the one in the y direction, whatever it turns out to be, plus something times the vector in the z direction, that would be exactly true here as here. In a sense, I've changed nothing. But this is really the way we prefer to write it, and this is really confusing. Well, what has changed here? Well, I've subtly added a point, the origin, and drawn my vectors so that they emerge and all have their tails coming out of that agreed upon origin. Well, I'm really talking about a different kind of quantity here. I'm talking about something that we call a frame. And remember, a frame was something that we got when we added, or an affine space, to bring it to that. We really haven't used the word frame much. But I convert from a vector space to an affine space by adding a point. And that point corresponds, when I look at this visually, to the origin. So I could say it's a vector space, but a plus I'm adding an origin, and then I have something which we call a frame. And so the word coordinate system is often used very loosely in this way with the origin, but people like mechanical engineers in particular are very good at saying, no, I'm talking about the frame. And generally the word frame comes from the idea of a frame of reference. And this is how we can now reference any point or any vector within that frame. So the vector space was insufficient, or a coordinate system, which is what comes from a vector space, is insufficient for representing points. But if we move to the affine space with the origin, then we can represent both points and vectors, as you'll see in the next slide or two. Okay, so how do we represent something in a frame? Well, first of all, we'll say what determines a frame. Once more, since the vector space is embedded in the frame, I'll have some basis vectors, v1, v2, and v3, and now I'll have an origin, which is a different kind of thing. It's a point. So a point plus the basis vectors will give me a unique frame, and now within that frame, I still have the vector space. So all the vectors can be written as alpha 1, v1, plus alpha 2, v2, plus 3 dimensions alpha 3 v3 for properly chosen alpha 1, alpha 2, and alpha 3. Now what about a point? Well, I'm going to argue with a point. What I can do is always go from the origin out to this point in space by a vector that goes from p0 to p1. So a point is, we use the notion of point vector addition. Any arbitrary point is the origin plus a properly chosen vector, but that properly chosen vector is going to be a linear combination of our basis vectors v1, v2, and v3. So I get this statement down here, that every point is the origin plus a vector, and that vector is written, I'll use betas now instead of alphas so we don't confuse the two, as some constant beta 1 times v2 plus beta 2 times v2, and in 3 dimensions, beta 3 times v3. So there's a distinction now between the representation of a point and the representation of a vector, where the representation of the point requires that origin here. And the problem which we get into, and will cause you this problem, and this will be the last thing for today's or this lecture, is that if there's a danger of saying the following: okay, here's a representation of an arbitrary point. Here's a representation of an arbitrary vector in that affine space. I think they look the same because each one has these 3 scalars in here. So if I look at the point, I say, why don't you represent the point as just beta 1, beta 2, beta 3, and then represent the vector as alpha 1, alpha 2, and alpha 3. The problem is, if I just give you these 2 representation, you don't really know which one is the point and which one is the vector. So if I give you 1, 2, 3 here, the point 1, 2, 3 and the vector 1, 2, 3, and this is the mistake that's made, I think, in the majority of books, whether they're linear algebra books that don't care about the geometry, or graphics books, they say, oh, well, we'll use this 3-element representation. But this is really gets you in trouble, because what's understood here in the representation for the point is that there's an origin you know about. And we all sort of agree in our head, so we don't write it down. But here's the problem. If you go back here to the little picture of the affine space, hey, the origin's right here. So this vector, alpha 1, alpha 2, alpha 3, it could be here, it could be here, it could be anywhere as long as it has the same direction and magnitude, no problem. But this point belongs in only one place because a point has a position. And we'll see some more examples of that later, and we'll see a way that will always get you around that problem.